In this lesson, we'll continue our development of the various rules you can use when taking derivatives. So we've already looked at what's known as the product rule, and before that we started with the most fundamental, which was the power rule. So now we're moving on to the quotient rule. So in this case, if I have written a quotient, which is the quotient of two functions, f of x divided by g of x, then the derivative of that quotient, which I'm calling q prime of x, is equal to, and it's a rule that you want to commit to memory if at all possible. It is the derivative of the first times the second minus, this time, if you're remembering the product rule, we had a plus here. So now it's the derivative of the first times the second minus the first times the derivative of the second. So that's very similar to the product rule except for the subtraction. But then you also have to take the second function, so the one that's in the denominator, and you keep it, but now you square that entire denominator. And of course, since we've got a denominator here, one of the things that's understood is that this function in the denominator has a restriction so that it is not equal to 0. And that restriction also saves us or protects us in the derivative, because the restriction still applies, so the derivative also won't have division by 0. Now, you may or may not need to use the quotient rule if you have a monomial in your denominator, because you can actually split things up. Now I'm going to go ahead and I'm going to use it regardless, but I'm also going to show you what that might look like. So here are two examples where you would have a monomial. And so what I'm saying is, in this case, this one could actually also be written as, let's do that properly, vertically. That could also be written as x squared over 3 minus 5x over 3. And now I don't need to really use the quotient rule in this case, because this is just a constant, and so I could actually just apply the power rule here. And in this case, I could rewrite that as x cubed over x squared plus 1 over x squared. And x cubed over x squared, well, that's just equal to x to the power 1 plus 1 over x squared. Now this is also interesting, and a bit of an aside. This is x to the power 1, whereas this one, you might write this as x to the power negative 2. And if you write it this way, you're no longer worrying about a quotient. You could actually just deal with this using our power rule. So there are some subtle things that come up when you're dealing with these derivatives, and it also shows you do have some choice as to how you choose to approach this. Of course, my expectation is that you are going to become proficient using any of these rules, but certainly when things are wide open, you can choose the path that appeals to you the most. Now in these cases, I am going to, and actually you can see I don't have a monomial in the denominator, so I have no choice. I'm going to use the quotient rule here, and so I'm going to, and I'll just write it over here at the side again. So if I have f of x over g of x, then my derivative, let's do it this way. If y equals, I'm just going to say f over g, then y prime is equal to the derivative of the top, f prime, times the bottom, minus the top, which is f, times the derivative of the bottom, which is g prime, all divided by g squared. Let's make sure we don't confuse our y with our g there. So we're going to do the same thing here. The derivative, y prime, is the derivative of the numerator. The derivative of 3x is simply equal to 3 times the denominator, unchanged, x squared plus 5, minus the numerator unchanged, 3x, times the derivative of the denominator. Now if you're not sure about the derivative of the denominator, we've got two terms here. The derivative of the first term, we evaluate that using the power rule. So the derivative of x squared is simply 2x, and the derivative of positive 5, that's a constant. The derivative of that is 0. We wouldn't normally write that 0 there, but I'm going to include it just this once. So the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom or the denominator, all squared. And now I'm going to expand and simplify the numerator. So I get 3 times x squared is 3x squared. 3 times positive 5 is plus 15. Minus 3x times 2x is minus 6x squared. And then negative 3x times 0 is simply 0. All divided by x squared plus 5, all squared. And so I combine these together, I end up with negative 3x squared plus 15 divided by x squared plus 5, all squared. And whenever you do something like this, you do want to make sure that you take a look at this numerator and factor it, just in case you end up with a common factor in the numerator and denominator that you can divide out. So the common factor here is obviously 3, but I'm actually going to take out a negative 3. So I can then write this as x squared minus 5. And that's an important thing. You have to be careful there. It's easy to focus on that denominator, and you almost want it to be x squared plus 5. But it's not, because negative 3 times x squared is negative 3x squared. Negative 3 times negative 5 is positive 15. So this is as far as we are allowed to go in this case. And just, of course, a quick reminder, which is there is a restriction that x squared plus 5 cannot be equal to 0. But if we actually take a closer look at this, this is a quadratic. X squared is always positive, plus 5. So x squared plus 5 is always greater than 0 anyway. So this restriction actually doesn't matter. And in this case, we can have x member of the reals. Oh, I skipped ahead. I wanted to, let's make a copy of that page. I'm going to need some more room to do the next question. I thought I already had a copy of the page there for that. All right, so I'll need to clear out some room here. So let's get rid of all of that work that we did on that other question. Sorry for the bit of the delay there. And now we are going to do part B. So for part B, to find the derivative of this one's a little bit more complicated, not terribly so. It's just the terms in the numerator and denominator are a little bit more involved. So once again, it's going to be the derivative of the numerator times the denominator. So the derivative of the numerator is 2x. The derivative of x squared is 2x. The derivative of negative 4x is just negative 4. And the derivative of negative 12 is 0. So I'm not going to write that this time. Times the denominator unchanged, x cubed minus 8. Minus the numerator, which is x squared minus 4x minus 12, times the derivative of the denominator, which is 3x squared, and the derivative of negative 8 is 0, so we just write that as is, all divided by x cubed minus 8, all squared. So that is equal to, I'm going to have to do an expansion here, and I'm going to have to do a binomial expansion using FOIL. A little odd because I've got that cubic, but so be it. So I get 2x cubed times, 2x times x cubed is 2x to the 4. And then I get minus 4x cubed minus 16x plus 32. That's the first expansion, minus, and I'm going to do this in a bracket, x squared times 3x squared is 3x to the 4. Negative 4x times 3x squared is minus 12x cubed. And negative 12 times 3x is negative 36x. I said 3x, I should have said 3x squared. All divided by x cubed minus 8, all squared. And that is equal to, so now some simplifying. I have a 2x to the 4 minus a 3x to the 4, so I just get a negative x to the 4. I have a negative 4x cubed minus negative 12x cubed, which is plus 12x cubed, so that's plus 8x cubed. I have a, let's see, minus 16x, nothing to match up with that. I have negative of negative 36x squared, so that's plus 36x squared. I have minus 16x, and I have plus 32. And that is all divided by x cubed minus 8 all squared. Now, I could go further with this. There are some things that I could try to do just to see whether or not, like if I really wanted to simplify this, there are some things I could do. The most relevant thing for you to keep in mind here is this, which is that x cubed minus 8 is actually a difference of cubes. That's actually x minus 2 multiplied by x squared plus 2x plus 4. So the question becomes, and so in that case, x cubed minus 8 all squared is just this factored form all squared. So now the question becomes whether or not either of these a divisor to the numerator. So that's the question we have to ask ourselves at this point in time. And these also would help to give us restrictions. For example, this also gives us a restriction, which of course says that x cannot be equal to 2 because we have to avoid this being equal to 0. Now, if we want to test whether or not this is a divisor to the numerator, I could check x equal 2 here. I could sub x equal 2 in here, essentially applying the factor theorem. And I could also perform some long division to try to divide x squared plus 2x plus 4 into that whole numerator. And that's an algebraic exercise. That's not the point of what we're doing here in this lesson. We've accomplished the point, which was to apply the quotient rule here, but I want you to understand you could be asked to, and you need to be ready to go further with other forms of algebra that you've learned in this course or in past courses. Okay, so moving on from there, find the coordinates on the curve of f of x, which is given here, where the tangent line is horizontal. The key here is this: tangent line is horizontal, and in particular horizontal. So let's actually look at this. Horizontal means the slope is equal to 0. And so tangent line is horizontal, of course, means the slope of the tangent is equal to 0. But we've talked about what is the slope of the tangent. Slope of the tangent is the same as instantaneous rate of change equals 0, and I'm really taking the long way to get here, which is going to be the derivative is equal to 0. All of these things, slope of the tangent, instantaneous rate of change, and the derivative being equal to 0, that means the same thing. So the first thing we have to do is find the derivative. What is f prime of x? And so f prime of x is equal to the derivative of the numerator, which is just 2, times the denominator, which is root x, minus the numerator, which is 2x plus 8, times the derivative of the denominator. And for that one, I'm just going to go to the side because I don't consider it to be obvious. So let's call the denominator d of x, and that's equal to the square root of x. Square root of x is the same as x to the power 1/2. And so that derivative, d prime of x, is going to be 1/2. I bring the 1/2 down, x, and now I subtract 1 from this exponent, and that's going to give me to the negative 1/2. And you might write that in a more simplified form. That's the same as 1 over 2 root x. And we will want to rationalize, but it's not always a good idea to rationalize right away, because something may come out of this to make you realize you don't have to rationalize right away. Now, looking at this, I don't think that's going to be the case here, unfortunately. And then that's divided by the denominator all squared. So let's go ahead and start to work with this. I just end up with 2 root x here. And now I guess I have to expand this out, which is going to be negative 2x times this. So that's going to be minus 2x over 2 root x. And then the 8, it's going to be minus 8 over 2 root x, all divided by square root of x all squared is simply x. So we're going to have to do some simplifying here. 2 root x, and maybe I can do some simplifying right here because I can see those 2's are going to divide out. Now what about this? I've got minus x over root x. That is the same as x to the power 1, and this one is x to the power 1/2. So overall, that ends up being minus x to the power 1/2. We have x to the power 1 minus x to the 1/2. The 1 minus a half, so we end up with x to the 1/2. And then we end up with, over here, I think I will go ahead and now rationalize this one. So this is just going to be times root x, not root 8, times root x over root x. And so this works out to be minus, I can also do this, divide out that, ends up with a 4. And so I end up with minus 4 root x over, and then I just end up with x there. It's still kind of awkward because now this whole thing is over x. So there are some more things that I could do here to try to simplify this. But we do need to keep our goal in mind. Our goal was not to take the derivative and simplify as much as possible. Our goal was actually to find out when is the slope equal to 0. So how are we going to accomplish that? And the way that we're going to do that is that we're going to, we're going to take a closer look just at the numerator. Now, before I move on there, I do have a simplification that can take place. I'm just going to take this minus x to the half, and I'm going to write that as square root of x. And the reason I'm making that change is because I want you to see, before I act on it, I have 2 root x minus root x, which is just 1 root x, minus 4 root x over x, all divided by x. Now I'm getting to the point where I could actually do something useful with this. And so that's what I'm going to do now, which is I'm going to set f prime of x equal to 0, and I'm going to solve. So I get square root of x minus 4 root x over x divided by x equal to 0. Now there's no way that this denominator can result in this being 0. So what I'm going to do is I'm going to multiply both sides by x, and I end up with square root of x minus 4 root x over x equal to 0. And I could do the same thing again, or I could put this in terms, I think I'm more comfortable doing this in common denominator form, but it would work either way. So I'm going to put this whole thing over this denominator x, and so I have to multiply by this by x, so I end up with x root x minus 4 root x equal to 0. And once again, I multiply through by x, and I end up with x root x minus 4 root x equal to 0. I have a common factor here of root x, so I'm now just going to factor that out. I end up with square root of x, x minus 4 equal to 0. And so this gives me two equations. One of them is square root of x is equal to 0, or I end up with x minus 4 equal to 0. And this one resolves to x equals 0, and this one resolves to x equals 4. But this is inadmissible, because we know, going all the way back, actually at a number of stages we've had x in the denominator, as recently as here. So x is not allowed to be 0. We have that restriction. So we can't do anything with that. And so we end up with x equal 4. And so is that enough of an answer to our question? X equal 4. We have to go back and take a look. Find the coordinates on the curve. So it's not enough for us to find x equal 4. We need a point xy. But that's the same as a point x, and the y coordinate is going to be f of x. And that is the same as the point, well, we want the point where x equals 4, which gives a y coordinate, which is f of 4. So what is f of 4? We go all the way to the original function just to remind ourselves of that again. F of x is equal to 2x plus 8 over the square root of x. F of x is equal to 2x plus 8 over the square root of x. So that means f of 4 is equal to 2 times 4 plus 8 divided by the square root of 4. 2 times 4 plus 8 is 8. So 8 plus 8 is 16. Over the square root of 4 is 2. So I end up with a value there of 8. And so that means the point, this value, is 8, as we just discovered. So therefore, the point where the slope of the tangent is 0 is the point 4, 8. Those are the coordinates of the point where the slope of the tangent is 0. And just to wrap up this lesson, I wanted to show you the graphical version. So here is the graphical version. Here is the function f of x, 2x plus 8 all divided by the square root of x. And where is the slope equal to 0? The slope is equal to 0 along this line, this horizontal line. You can see it has an x coordinate of 4 and a y coordinate of 8. What did we do? Here is the function, the derivative of the function, f prime of x, in a slightly different form than what we ended up with. This is what GeoGebra gave me when I took the derivative. But you can see from this, where does this derivative cross 0? So we found where the derivative was equal to 0 is where the original function has a slope of 0. And we solved the derivative to find this value. And that's it for this lesson. Really, just another mechanical rule, a little bit more complicated. The presence of that denominator can complicate things, but otherwise quite straightforward.